Welcome. My name is Kathy French. I'm one of the faculty members here in structural engineering. I'd welcome both people here in person and online. Today is a very special day. Annually, we have a lecture devoted to the memory of Professor Robert Dexter, who actually passed away some 17 years ago. It doesn't sound that long ago, but this week. He was an outstanding faculty member, all around, very famous for his work in fatigue and fracture. Before I introduce our speaker today, I'd like to first recognize our scholarship winners. So we have a Dexter Scholarship winner, and Professor Lauren Linderman is going to make the presentation to that winner, and she's the chair of the scholarship committee. So Professor Linderman.
Thank you, Kathy. It's my honor to present the Robert Dexter Scholarship, who's the honor of a student who has great scholastic achievement while participating in professional organizations and contributing to the community of the department. So it's my pleasure today to give this award to Nahum Yelizarov, who is a transfer student here, who's very involved in the department. He participates in ASCE, as well as our outreach coordination, among other things, and you'll see him all around the department. So congratulations.
Thank you, Lauren. And now, without further ado, and also congratulations to Nahum. I also had him as a student in my class and can vouch for him as an outstanding student as well. It's my great pleasure to introduce our speaker today, Professor Hussam Mahmoud. He was a student of Professor Dexter. He came to the University of Minnesota for his bachelor's and master's degrees. And following that, he went on to the University of Illinois for his PhD. He has worked in the laboratories. He managed the NSF Nice Center at the University of Illinois. He was a research scientist at Lehigh University. And he's been a member of the faculty for 10 years now at Colorado State University, where he's the George Abell Professor and also Director of Labs there. Hussam has more than 100 refereed journal publications. He's served as chair of some very important technical committees, including the ASC Technical Committee on Steel Bridges, and also on fatigue and fracture. And I think one of the most interesting things that I found, which is characteristic, I think, of Hussam, is he was recently awarded, it's the National Academy of Sciences, Engineering, and Medicine awards for a cohort on emerging leaders of the future. They select 22 people from among 300 applicants from all fields of science, engineering, and medicine, and also industry and as well as government agencies. And so he's been selected as one of those 22 people. And they want emerging leaders who can coalesce their ideas and think about the future. And so I think our future is in great hands. So without further ado, I'd like to introduce our speaker, Hussam Mahmoud.
Thank you so much, Kathy. Thank you. Thanks a lot for the very kind introduction and for the very, very kind invitation. This is home for me, of course. As Kathy mentioned, I did my undergrad and I did my master's here, and I made a lot of noises as a student, so some of you might remember me. So it's really great to be back on campus, and it's a great honor to be presenting this lecture for Robert Dexter Memorial. I'm going to talk about advanced methods for performance-based assessment of steel buildings under fire and fire-following earthquake. Before I start, I'll just tell you something really interesting. When Kathy told me about this presentation, and I started to kind of look at where the presentation will take place, because it used to be in a neighboring building here, I found that it's going to be in room 210. The first time I ever met Robert Dexter was in room 210. I took linear structure analysis with him back in 2000, and around the same time, look at the time where the lecture was roughly between 10 and 11. And I remember halfway during the seminar, or during the class, at one point, I came up to him and I said, Professor Dexter, I'm in your class, as you know, can I work for you in the lab? And he said, well, do you have any lab experience? I said, no. He said, do you have any work experience? I said, no. He said, do you know how to use any tools? I said, no. And he said, okay, you're hired. And that's how it all started. I had an incredible relationship with him, even though it was for 4 years when I did my master's and when I went to Lehigh University. But I can't even describe how strong that relationship was. It was remarkable. I just remember Dexter as this guy. I mean, if you look at him, you'll see how nice and approachable of a person he was. And he was really willing to share all his knowledge with all of his students and colleagues, and just a remarkable, very peaceful guy. That relationship actually was instrumental in me getting tenured at Colorado State University. When I left, some of you might remember this experimental setup in the lab. That's what I did for my master's. When I was at Lehigh University, I worked with him on this NCHRB project on inspection and management of bridges with fracture critical details. And then I got involved with him on this project for the Army Corps of Engineering. And we were writing this report on fitness for purpose assessment of hydraulic steel structures. And then we submitted the final draft report, and he died. And then, long story short, about a year and a half after that, the Army Corps reached out to me saying, your name was on the draft report, can you finish it for us? And I said, sure. And I worked with them, and we finished it. And since then, it has been non-stop work with the Army Corps for the past 15 years. We do experimental work and numerical simulations for them every single year. So there have been a tremendous collaboration with them, and one of the main reasons why I ended up getting tenured at Colorado State. So even though he's gone, but he continued to look after me, I would say. Today, I'm not going to talk about fatigue and fracture, because that's one area that I work heavily on, and I've learned from Robert Dexter, but I'm going to talk to you about fire and fire-following earthquakes. So here's the outline of the presentation. First, we'll talk about some motivations, and then I'll tell you some of the work we've done on system-level analysis and component-level analysis that kind of promoted the performance-based design approach that we looked into. And then how we might take this to a community-level analysis, then if we want to look at a community-level behavior. We've done it the community level for wildfire, but the translation to fire following earthquake at the community level is quite clear. Then we'll have maybe some conclusions. So the motivation is there are a lot of fires that have taken place in the US, and this report was released in 2020 that shows tremendous social losses. Casualties are very high, and very, very high number of dollar signs on these direct losses. And you can see that the WUI, which is a big deal, and you hear quite a bit about WUI fires or wildfires, is only 19% of that. So fire at the building level is very important. Of course, at the community level is obviously critical for certain states. The problem right now is that traditional building standards specify a fire resistance rating. So they say you put insulation on your beams and members, and then maybe that will last for a couple hours. And so that allows you enough time to either distinguish the fire or to leave the building. The design provisions, on the other hand, they're very simplistic. They improved, but they're very simplistic. They're not intended to be at the system level. It's not a criticism of the current fire provisions, but they're not meant to do that. So a lot of work needs to be done to understand the behavior of buildings under fire following earthquake. There has been large developments in Europe, but we need to do a lot more in the US. If you look now at historical events, you'll see, for example, the Meridian Plaza in 1991. There has been tremendous damage because of a fire that ultimately caused no collapse, but there's large buckling of beams as well as large damage in general, but columns were in good shape. But if you look at cases where collapse did happen, and in this case it's partial collapse, you'll see that there was collapse triggered by buckling of the column, as you might expect. So column behavior is really important. That's not to mention that connection behavior is not important, because what happened in World Trade Center 7 in 2001 after the terrorist attack is that we ended up losing one of the connections, the effective length of the column increased, and the column became more susceptible to buckling. But there has been some very limited studies that said, the performance of buildings, steel buildings, under fire, for example, is not does not have to be as drastic as we might think. We might end up with large losses, but not necessarily collapse. And this test was done in the UK in 1991, I believe. And you can see from the test there's tremendous canary actions that allows you to distribute the load and take advantage of that tension fields that are developed. Now, at the community level, we've seen, just as an example, there was major fires after the 1989 Loma Prieta earthquake. Of course, there was one after the 1916 earthquake that completely destroyed San Francisco. But this particular one, giving the improvements in fire regulations and so on, still caused tremendous damage. And the fire spread because of the wind speed and direction and building density and material and so on. If you look at wildfire, there's very similar characteristics, not necessarily in the initiation of the fire, but in terms of the fire propagation. Fire will jump from one building to another because of the wind and the material and the direction of the wind and the wind speed and so on. I had a project with NSF to look at the campfire after the 2018 event, and it was just like a war zone. I can't even describe it. So what is it that we're trying to get out of these sort of models that we want to develop to understand how to handle this problem? This is one way to think about it, not necessarily the only way. So my way of thinking about it is we need to ask what is the time that we can have to escape. Because if there are people in the building or even firefighters that go inside a building, it's very important to understand what are the safety of the firefighters would look like and how safely can they evacuate people from an actual building. At the community level, it's very similar because evacuation at the community level becomes very important, and you need to understand how much time you have and what are the resources that can allow you to distinguish the fire and get out of the community as soon as possible. So it's a time-dependent problem. It becomes very important to understand the time evolution and how that impacts the building level behavior and the system level behavior. So we started by looking at system level behavior, and I usually get my graduate students warming up with kind of simple finite element models to allow them to understand the problem, understand the literature view better, and get their hands kind of going with some modeling. So we started with simple models of moment frames. These moment frames represent the SAG buildings. This was a big project that took place in the US after the 1994 Northridge earthquake. And we've modeled the buildings with the mass and stiffness and everything else, but instead of using the moment connections that were in the SAC, we used reduced beam section connections by discretizing the element sizes to represent the reduced beam section connection, and we implemented a panel zone model, of course, as part of the model. And we took the modeling level just slightly higher by saying, let's do a multi-resolution model, where the bottom connection here is a 3D finite element model of that reduced beam section connection that allows us to reflect on the stress concentration and how the stresses and yielding is developed in some of these details. And of course, we had panel zone also models for beam column connections at different locations. We modeled the gravity system using this linear column with MBC links, for example. I'm not giving you a lot of details because that's not where I want to emphasize the details yet. You look at different scenarios, different fire scenarios. You could have fire in the first bay or the second bay, in the second story, and so on, with a lot of variations in the fires. And you incorporate the proper material properties and material definitions, and you model you insert your time temperature curve either as monotonically increasing, which mimics this ISO 834 Euro code, which is similar to E119, which is what we have in the US. It's only heating, but that's not realistic, so we also used heating and cooling using the Euro code parametric fire curve. So you can do a lot of analysis. And after we do this analysis, we started to look at some of the results. So you can see the results shows, for example, when you look at the axial load in some of your columns, and you can see what happens with heating and cooling. You can look at the stresses as a function of temperature and how they change with heating and cooling as well. And you can look at the axial moment interaction, and you can see when you violate the envelope for axial moment interaction for the AIC moment interaction curve. So you can reflect on the results. With that multi-resolution model, you can also look at the behavior of the connection. You see when yielding happens and where. But is any of this relevant in terms of system level behavior. Why do I care if the connection yields? Well, of course it has to yield, it's fire. But what is the impact of that on the system behavior? So when you look at the system, global system level behavior, and you reflect, for example, on the inter-story drift ratio, which is a very known parameter that we look at when we look at the performance under earthquakes, for example. If you look at these different earthquakes, which we grabbed from the Peer Center in California, scaled properly and everything, and then you run the earthquakes on these models, and then followed by the fire. Notice something very interesting with different fire scenarios that I'm not describing, but really the fire following the earthquake is not necessarily giving me a big impact on the inter-story drift ratio, right? So it's not necessarily a wrong parameter to look at, but it should probably not be the only parameter to look at. This suggests that fire following earthquake is not important. And actually, the similar results, I just saw a presentation a couple months ago, was presented by someone I know, almost identical in terms of their conclusion. But maybe the inter-story drift ratio is not what we should be looking at, right? So we said, okay, well, let's look at something that allows us to understand the behavior, even though it's complex, a little bit more, right? And somehow put time into it. Well, the problem with these models, if they don't converge, you say failure happened. Well, conversion is not just an indication of failure in finite element models. And if they do converge and continue, you think what you're getting in this nonlinear state is quite accurate, which might not be the case either. So you have to be very careful with these models. So we said, let's take it a notch up. And we developed a 3D finite element model, and this was done by my master student, Chow. And we looked at different time temperature curve, different cases, again, heating with no cooling, and then the heating and the cooling. This particular one has a fire in one bay, because this allows the building to not just collapse ultimately, but also rotate as it collapses, right? So what does that torsion do to the failure of the connections? And this, of course, will promote more of like a vertical downward failure. There's a lot that goes into modeling this, and it was actually very challenging to get this to work. But you can look, for example, as one example, modeling the connection. We found some work that was done by Suraj that indicated that you could represent the shear tap connection with these different springs that represents the plate bearing, shear, and beam webbing bearing, and so on. And if you put it all together, while taking the work by Rex and Esterling into account to allow for the changes in bearing, bending, and shear stiffness as a function of temperature, then you could be able to model the behavior of this connection without doing a very detailed 3D finite element model. And actually, we did a lot of validation on this stuff that I'm not showing here because of time, but I have slides at the very end of it, in case anyone has questions on validating any of these models. The moment connections, we looked at the stiffness of the connection as a function of temperature, and we also include that as moment rotation relationship in our models. And we impose 0.06 radiant rotation that at the onset of failure, to model failure. And this value, threshold value, comes from the literature. And then we, of course, put the outer straightness and some of other models, contact between elements. We modeled the concrete, which I'm not showing here, slab with embedded steel in it, using damage elasticity model for the concrete, and so on and so forth. A long story short, what you could do with this model is something like this, where you can start to reflect on the behavior of the system as a function of time, and we slowed down the simulation so we can see the collapse, and you can see the collapse, and you can see what's failing and what's not failing. You will notice through this failure is that separation and failure of elements and connections only happens when you actually collapse the building, because it's coming down vertically. There is no inter-story drift that promotes failure of the connections, right? There are other scenarios that might promote that, okay? And if you have an inter-story drift after an earthquake followed by a fire, that might cause the inter-story drift to increase. I'm not saying inter-story drift is not important, but I'm saying column buckling we found to be obviously very critical for us to start with. But if you reflect on some of the results here, and I'm just showing a snapshot of that, you can see that we have displacement as a function of temperature, and so the displacement of all 9 columns at the first floor as you increase your temperature, and you can see when collapse starts to happen around 650 degrees. And for the different 4 cases, this one is coming back because you have this rotation and the building comes back. And if you look at the axial load divided by the capacity, you can see that you're violating a value of 1 at temperature less than the temperature in which the building starts to collapse. So at 600 degrees or even more, you start to get a number of columns violating P over VPN, which implies, right, that before I collapse, I've already violated the axial load capacity for 1, 2, 3, or 4 columns. So if I go look at the code, again, the intention of the code is not to inform you on system level behavior, right? But the code tells you here's the capacity of 1 column. From a system level analysis, I can't do anything with that, right? So this tells me that it takes multiple columns for the building to start to come down. And this information is very important because a firefighter can go in, and if they understand when the building might collapse or might not collapse, they know how much time they have to evacuate and help people, right? Rescue people. So it's very critical to do this type of analysis. We reflected on column behavior even more to try to do some experimental work to get some data out so that we can validate our models later. And so we collaborated with the University of Toronto. Hussam Mahmoud at Toronto, he's actually my very good friend. We did PhD together at Illinois. And we did hybrid simulation under fire and fire following earthquake. So if you look at the typical hybrid simulation formulation, you will have to get rid of the mass and the stiffness and the damping in your hybrid simulation formulation. So the model, we looked at small scale braced frame. This is the experimental component of the model. And this is an Abacus finite element model that we developed. And we did all this work at Colorado State using some of the hybrid simulation tools that Osang developed at Toronto, which is the Nikon that he developed for communication and for checking the error and tolerances and stepping through the equation. So ultimately, we can combine this together in a hybrid simulation to look, you have a physical behavior of the system, the entire system, but you also have experimental results. We developed this experiment at Colorado State University where we modeled, where we had one actuator that is applying the load on this column, and what you see around the column is basically the heat panels. We had 4 radiative thermal heaters making kind of like a square. The column is right inside, and we had thermocouples. We had a PID controller to generate the predefined time temperature curve. And we had only in-plane buckling of the column. So we're doing this brace system that is sort of guided by these 2 columns to prevent out-of-plane buckling of the column. We also put a pin connection at the bottom here to impose an initial interstory drift that comes from the finite element simulations that allows us to not just apply the load under completely vertical column, but also with different level of interstory drifts. And you can see here the experimental setup that we had, the pin connection that we had for this model, and some of the thermocouples that we installed. And as I mentioned, the Nikon was used to record the data received from the controller and stepping through the time history. If you look at some of the results for the different tests we had, and again, this is hybrid simulation. This is not just the experiment by itself. We did different tests, hybrid simulations with different interstory drift for the column. And you can see how the interstory drift, as it increases and as you go down the table, it has a big impact on how the displacement develops over time, and more so on the axial load over time. So column buckling is very critical for us. How can we take the information we developed from the system level behavior and from the single component level experimental analysis to further reflect on component level behavior, right, for the columns? Because now we feel like we need to do more on this column analysis if we want to develop performance-based design framework. So we decided to develop a flexibility-based model to be able to understand the impact of fire and fire following earthquake on columns. And you could do that, of course, with finite element analysis. You can build an Abacus model and allows you to do that. But if you want to run thousands of simulations to probabilistic analysis, it becomes very difficult. You can, of course, write a code that allows, Abacus to talk to something else to update your models and run it, but we choose to develop a flexibility-based model to do that. So this was all done in my MATLAB, and again, it was done by my PhD student, Mahmoud. And you look at the kinematic equations and equilibrium equation and constitutive equation described by these 3 equations, and these are reduced forms that allows you to get the nodal displacements for these columns. And you can take these displacement and relate them with, have eta that relates the vector of relative displacement and rotation to the vector of the applied redundant forces. And then you can get your full vector of nodal actions and deformations. And from that, you can easily extract your stiffness and geometric stiffness for the system. And these stiffness values are very important for the stability analysis. one of the most important features of this flexibility-based model is our ability now to model the models of elasticity for the column in this sort of using this sort of variability. So we take the column, when we discretize it into small little pieces, and these small little pieces can have different variation of the model's elasticity. And that what imposes the temperature or the fire temperature profile of your column. So if your column have a linear profile or a parabolic profile, you can actually impose that on your column with these variations. You will see a lot of work that has been done on behavior of beams and columns under uniform temperature, but not under this varying temperature profile. But this is a very quick tool that allowed us to do that. And using this tool that we developed with different material models, this was we got from the Euro code. This is Amit Verma and his student at Purdue, Elastic Perfectly Plastic, and our work at Colorado, which is model D that has trilinear representation of the stress versus strain. We are now able to look at the behavior. But we had to include, of course, P delta effect because of on the column, because of the curvature or because of the bending you get on the column. And we also included residual stresses in our model that comes from thermally induced residual stresses from hot rolling process. And so you can look at these different profile for temperature and the cool end versus the hot end, meaning this is colder than the other end. And with these different temperature profiles, you have a variation in models of elasticity, you have a variation in the yield stress, and you have a variation in the proportional limit. But it gives us this probabilic versus linear variation in temperature. When we run our model initially with constant temperature, there is no temperature variation along the length, and compare what we get versus what everybody else got, you can see that at 200 temperature, or 200, 400, 600, and 800, we get very similar results to what Amit developed at Purdue with his finite element. I believe they used the abacus. So our model is getting, that flexibility model is giving us very similar results to what you would get out of abacus. And so that was very good way of verifying that the models work. Now that I'm able to impose different variable temperature profiles, I can now show you how the different profiles will end up giving you different critical buckling stress as a function of the KL over R, the slenderness ratio for the column. So you can see as temperature profile changes, the critical buckling stress changes accordingly. And this becomes important later when we try to couple this flexibility model with the big finite element model. So we used now this flexibility-based model to propose equations for design, because the current AIC equation do not take into account the varying temperature along the length. They're only supposed to give you predictions for uniform temperature. But now we can get, for any temperature that you want, we can actually get the F critical. Which is the critical buckling stress. And because our model is able to take the inter-story drift or as well, we're able to develop an equation that allows us to get F critical as a function of when you have non-uniform temperature and inter-story drift. And so we propose these two equations to allow you to understand column buckling under these two different conditions, with and without an inter-story drift in the presence of any temperature profile. And we compare that, our proposed equations, with what we get out of our model, and we get excellent results. And now you can see how F critical is drastically influenced by not just the temperature profile as I showed you, but also by the inter-story drift that you have in the column, which is very important to look at that from a component level. From a performance-based design, now how can we take the abacus models we developed at the beginning, and how can we take the single column model and put it together? So we started by looking at this 3-story sack frame, and we said this is the flexibility model. This is the steel model that we developed from abacus, and can we develop a performance-based design framework for that? Without getting into the massive details of how this sort of communication and loop worked, but I will show you the main components of this framework. So this is the performance-based design for earthquake that was developed by the Pearce Center. And everybody uses this performance-based design approach. For the problem that will, for any performance-based design, you have to look at the hazard, the system, the damage, and the losses. And for required performance, specifically for fire, insulation, integrity, and stability becomes important. So our focus was on stability. This is the model that we developed for performance-based design. And one of the most important features of this, I'll talk about all the other features as we step through it, but the fragility functions giving you the probability of the damage measure, fire following earthquake, giving the engineering parameter under fire, and that would be, for example, fire load density, and the damage measure in the earthquake, that would be interstory drift, right? So if I know the fire load density and the interstory drift, can I get the probability of damage for fire following earthquake? And so to do that, we had to do stochastic analysis. So we started by looking at the different random variables that correspond to fire load density, opening factor, thermal observability from the Euro code, and we get the mean and coefficient of variation, and we look at the different distribution. This allows you to develop a wide range of time temperature curve for different fire load densities. And this is for 500, for example, this is for 1,000. The other thing that was very important for us to develop is to look at the insulation. So we looked at the thickness, the conductivity, specific heat, and density. And there are various distributions that you can find for these in the literature. And using this finite difference analysis, you can determine what is your temperature in steel based on these temperatures that we got here, because the temperature in the steel is not the same as the fire time temperature curve because of the insulation. The temperature in the steel has to be different. So this allows us to get you the exact temperature in these columns. And then we looked at the famous work by Professor Galumbos to look at the combination of the mechanical load and fire for fire design as one of our variables. And some of the work Professor Illingwood also did on the combination of dead and life load. And then we have some sort of distributions that we used for the load as well. Ultimately, long story short, you can evaluate your G of X function as a function of fire load density, and then with different, this is for 3% interstory drift. And what you can get out of this is with different interstory drifts is the probability of failure versus fire load density for different interstory drifts. So this is essentially what I showed you on the bottom, and I said this is a very important equation because it essentially tells you what's the probability of damage. How do we put this with a building level analysis, right? Now, because this is still a single column, it doesn't tell me much. So it tells me quite a bit, but it's not enough. So we looked at the 3D SEC frame. Each column in this SEC frame is modeled using our flexibility model with the different stiffnesses that vary over time depending on the time temperature curve we get from this particular. So I ran a heat analysis here. That heat analysis is giving me different flexibility or different stiffness values for my column at the ends. And at the same time, I have the temperature profile for each column that I can impose on my columns using my flexibility method. And then I can then combine them together by first assuming, first I get interstory drift ratio under all earthquakes. So I have 10 earthquakes with 10 correlated set of interstory drift ratios. And then I impose different scenarios, not just the variation I showed you at the beginning. We're able to generate 5,000 scenarios of fire. So in MATLAB, we go and randomly generate a combination of zeros and ones that tells me this bay is on fire, this bay is not on fire. And using these values of zeros and ones, I can determine which columns are on fire or not, and I can take that into my MATLAB code and then start to evaluate the buckling load of this particular column. And then once you get the probability of failure for every column, right, using the temperature profile from here, using the flexibility method, you can compare that value to a randomly generated value to determine the probability of failure in each one of your columns. So ultimately what we can get is a probability of exceedance versus fire load density. So here, the onset of damage or instability in I number of columns or more in a given story. That in itself is not enough yet, because I'll go back, we haven't closed the loop entirely, but I'll go back and I'll tell you what needs to happen next is that we need to take this particular model that simulates the collapse and understand how long it would take to collapse and couple that model with the probabilistic model that we developed, target failure probability for fire load, and then go and tell firefighters with their thermal cameras, if you reach that value of fire, get out, right? And of course, you have to impose factor of safety on it. So this will tell me the number of columns that will impose collapse, and this will tell me the probability of failure of these columns. But I need to take this fire load density and communicate that to the firefighter, right? And say, when you have that fire load density at different locations, 4 or 3 or 5 columns, then get out. We haven't closed the loop here, but this allows us to communicate that to them as a function of time, when they should leave the building. Now, how do you take this to a community level analysis? Let me see. Let's froze a little bit. Okay. Just need to make sure we have time. Okay, so I'll step through that quickly. For community level, we started by looking at wildfire as a major problem. And like I said, it translates really nicely to fire following earthquake. But I'll focus a little bit on the fire at the community level from a wildfire perspective. The different stages for wildfire, you can go from ignition to propagation to ember attack to propagation at the community level. And we started developing a model that allows us to understand fire propagation in the wildland, not in the community. And we developed a cellular automata model that considered different burning rates of vegetation, captured the effect of wind speed and direction, considered the effect of topography, and ember generation and flight pattern. There's a lot to this that I will not talk about because of time, but I'll focus at the community level. But I will tell you why this is important to look at. If you look at this particular model, you can see that we can model, this is a plan view of the forest, and this is a lake, and there's a lake, we can model fire propagation as it progresses. And if I just go back quickly, you can see the spotting that happens because of the ember. So there's an ember model here. But and this is a variation of wind direction and what it does to this ember attack. The importance of this is that it gives us an indication of the fire intensity at the community level. So now imagine I have a community with different fire intensity that comes from my wildfire model. And this different fire intensity at the boundary of the community will obviously have an impact on the initiation of the fire. So look at, for example, your objects in the community. You can think of these nodes here as boundary nodes, and these boundary nodes will have a probability of being ignited for a given fire level intensity that comes from this boundary, the boundary with the forest. And if I was interested in this blue node, this node is essentially the structure I'm worried about, hypothetically. The fire has different ways to get to this particular node, right? And so you have to calculate weights for each edge going from your boundary nodes to this particular middle node. And these weights depend on fire propagation or physics-based fire propagation models. And then identify the most probable path, because not all these paths are probable. And then once you identify the most probable path, then you can actually calculate the probability of ignition for the most probable path for each boundary node to understand the probability of igniting your node in the middle. There's more to this, of course, that I can describe here, but we started by looking at Fort Collins. This is actually where I live. I wanted to make sure that my house will not get on fire. And we developed this graph, but you can see how much more complicated that graph is for actual buildings. This is a graph model that we developed between only these 3 buildings, right? It's a very complicated model. We call this model actually AGNI-NAR, Asynchronous Graph Nexus Infrastructure for Network Assessment of Buoy Risk. And the reason why we called it this is because AGNI, so my student Akshat told me that AGNI in Indian means fire, something like that. And NAR in Arabic, where I'm originally from, means fire. So fire, that's the name of the model. So we started by looking at classifying objects at the community level, buildings, roads, and so on, and grassland. And then the ignition probability between 2 nodes will have to be defined by the minimum of the total probabilities. It could be radiation from one building to another. It could be ember, or it could be conduction. But conduction within a given building, we assume that once building on fire, it's gone, right? So there is no conduction. That's why this is kind of taking out. But these are the different probabilities: radiation, ember, convection, driven by wind, and so on. I am not going to list the equations because they're very long and extensive, but some of this based on our development and some of it comes from the literature. So convection model is a function of the distance between the nodes, the effect of wind, flame heights, flame angles. The ember model is a function of access probability, if you can see the building or not. If the ember is flying, can it hit the building, or is it obstructed by something? The effect of wind direction, and as well as the wind distribution. And then the ember distribution is a function of volume of node, what you're burning, the tree, how big is that volume of node, distance between nodes, and wind velocity. And you can describe that ember distribution with this figure here, which comes actually from the literature. Our radiation model that we developed, we used the Stefan-Boltzmann law, which is very known for radiation. But instead of just looking at surface and surface that is not related to buildings, we actually took that, which is a function of the area, view factor, emissivity, and temperature, and we applied that to two neighboring buildings. So now you can imagine you can develop independent view factors due to surface inclination, and you can ultimately get the net flux on each surface, the net heat flux on each surface, which is the sum from all surfaces, right? So I can ultimately get the net on each one of these surfaces and develop a radiation matrix from one building to another. And if I take the transpose of that, I actually interestingly get the impact of this building on this building in terms of radiation. So this was pretty cool. That allows us to do radiation at the community level. And so when we apply this to community, for example, we can calculate the probability based on all these probability we have. We can calculate, and based on the most probable path that I mentioned, we can calculate the vulnerability from all sources, and we can calculate the total community vulnerability value, just for the entire community, if you want to communicate it as an average probability or average vulnerability for the whole community. You can then start to look at communities, and you start to evaluate what is the vulnerability for communities. So this is Oakland, California. It was struck by a wildfire in 1991, and we can look at the origin versus destination and determine the most probable path, right, that the fire would go to burn the structure. So very important information. We can also calculate the vulnerability for the different parts of the community. We broke it into region 1 and region 2. And we got actually really interesting results. The most vulnerable location in our analysis coincided exactly with what firefighters said in their reports, that these areas, when they ignited, everything went haywire. So this is really cool information for mitigating such large problems, which I'm not showing some of that here. One of the most important findings also, which correlates well with the literature, is that if you look at these different sort of map of the community, these small little things here are not buildings. They're not an actual residential home. Those tiny little objects here. And we find that using transitivity or clustering coefficient, we find that these small little objects that have a mean area of less than 10% have tremendous contribution in terms of the vulnerability, right? So they're so important. That's why firefighter fire codes tell you to remove anything in your backyard, remove logs, make sure everything is clean. So they have tremendous impact. At high wind speed, they're not important because ember takes over. At low wind speed, they become very important. We then took this, and I'm missing a lot of information, but just to give you a general picture, we took ignition maps, the cold danger map. We converted it into a probability of ignition. We take our wildfire work at the forest level and then at the community level, and then combine them together to get a total risk at any given day. And remember, that risk is driven by so many things. The community layout, the proximity of the building, all these probabilities for the different fire transmission mechanisms, the wind direction, wind speed at a given day. So this is a small slide, and just I'll describe it, but just so you can understand. We have the probability of ignition for year 2007, 12, and 17 for May until September. And then we have the community vulnerability from our model using the wind data that we download from NOAA, and we can get vulnerability from May until September for every single day of the month as well. And then you combine them together. We did this for different communities. I'm showing you two examples. Then you combine them together to get the total risk. And so firefighters at least have a way of understanding what risk is at a given day, right? So now that you know what the total risk is a given day, now you can take the same model, which I'm not showing you how we did it because this is just another animal in its own. But now we actually took this fire model that we developed, and we turned it into a fire propagation model. And we're getting beautiful results matching the campfire of 2018 in terms of the propagation pattern and the time it took for the fire to propagate from where it ignited, because we have that information, until it reached the end of the community. And this is tremendous information, because now you can start to think of how you develop mitigation strategies to evacuate, to slow down the fire, and so on and so forth, right? So this is work we're wrapping up. We're submitting a paper on that very soon. So at the end, I just want to tell you that our work on the fire and fire-following earthquake at the building and at the community level represented by the wildfire is intended to give us a behavior in a good, reasonable, approximated way, and allow us to understand the time it would take to evacuate the building or the community. So in conclusion, I just have one slide for you. Performance structures under fire and fire-following earthquake is very important. We are developing new methods for assessment of steel component and system under the combined events. And we develop new performance-based design to determine the probability of exceeding specific demand. And of course, our work on the wildfire is gaining a lot of attention. Actually, there is very strong interest in that work. And at the end, I want to thank you again for this wonderful opportunity to be here and to talk to you today. Thank you.
Thank you so much, Hussam. That was a lot of information, in fact, in this time, a tremendous amount of work. We have some time for some questions now from the audience and from online. Mary will monitor that. Vaughn?
A great talk. Thanks very much.
Thank you so much.
I want to ask about the kind of probabilistic model that you had for the helping the firefighters was a kind of prior model. Is there any kind of opportunity in the future, or how far away is having a just-in-time model where a fire goes off and the sensors in the building feed a model that immediately calculates what the progress of the collapse might be?
There's tremendous opportunities for integrating advanced sensors with these particular models, because there's even it comes from autonomous vehicles that are evacuating people automatically from their homes, to having sensors that will essentially detecting the heat that you have in every one of these columns, for example, that it tells you, firefighters, you must run out. Of course, residents, once there is a fire, they should not stay. But if you're in a situation where you have to be evacuated, right, firefighter who's evacuating you. And right now, it's actually a major problem. I don't know if how many of you know this, but sometimes the fires are too intense. The firefighter says we cannot fight this, right? So the models that we develop at the building and at the community level will allow you to reflect more on the level of danger in these cases.
But, no, I suppose my question is directly related to how long do the models actually take to compute, and is there an opportunity that you can run them in real time?
Sorry, yeah.
Or does it have to be done?
How long does it take for the model to compute? That collapse model, of course, was pretty heavy one. It took 6 hours for each case. But the flexibility-based model, it takes seconds to compute. The community wildfire model will not probabilistic analysis. If I model fire propagation not probabilistically, literally takes 2 minutes. But the finite element analysis is because of the nonlinearity in material and inelasticity in the material and geometric nonlinearity. It's just computationally very expensive. Yeah.
I have a question with respect to your first part. The essence is that there's interplay of mechanical loads and thermal loads matters a lot, and I think it's a lot of the thermal load is done with simulations. But I think you alluded also to experiments, right, where you can actually have the thermal component implemented. So my question is, what is the state of the art of those experiments? And from a facility standpoint, what are the requirements to actually have a successful experimentation in that respect?
Great question. This is actually a great question. So there's 2 ways you could do this. You could actually generate fire using actual flame, or the way we did it is using ceramic heat panels. And we took advantage of the great knowledge that was developed at Purdue University by one of the faculty there, Amit Verma, and they used that. Now, whether you use these panels or use actual flame, one of the most critical things is the ability for you to generate the time temperature curve that you want because of all the heat losses that you have. So we had these 4 different panels that are generating here that did not match exactly what we wanted from a time temperature curve. So, and in fact, I had a slide that showed what what is the time temperature curve that we got essentially. And that was the time temperature curve that we used in the lab and used in the Abacus model in the hybrid simulation. We need to figure out a better setup to prevent these heat losses. And if we're able to do that, then we have what we need. From a facility and regulation perspective, it was super easy to do that at Colorado State because we're not generating actual flame, right? And we had something in the lab that says, high temperature fire and we had some fire distinguishers on located at different locations, but it's much, much easier because there's no flume, there's no gases that gets produced that you have to worry about. If you're applying high temperature to something that is going to produce some sort of released gases that might be an environmental problem, that could be an issue. But for the steel column that we were testing, that was not a problem. So it wasn't difficult at all from a regulation perspective. Yeah.
We have a couple more questions.
Okay. Thank you for a very good talk. I have two questions. The first question, you mentioned about the fire following earthquake. I just wonder what is the state of the art on the understanding of the constitutive model of the material which is damaged first, then we heat it up. Is that different from the intact material being heated?
Okay, so a material damage first and then heated.
That happens
Yeah.
earthquake, a fire after earthquake.
Okay, so this is definitely a very good question. In terms of in terms of the behavior for material damage first versus damage then heated,
Yeah.
we've done that at the column level when we assume that the damage is a plastic hinge at the bottom of the column. But for different material, that becomes completely different. It's not as simple as that. For fire or fire following earthquake, or for fire following earthquake at the community level, or for wildfire, the most important thing is ignition. Once you ignite the building, how does the fire jump from one building to another becomes very relevant. So now you have to simulate, if you want to simulate the fire propagation inside a building and how that develops and how that fire would go from one building to another, but be more detailed on the damage inside the building, you can develop this model. Those are fire dynamic models that exist out there. But in terms of structural behavior of material under damage followed by fire, there's hardly anything out there at all.
Okay.
Yeah.
The second question is in the first part of the talk, when you do finite simulation, I guess you're considering compartment fire. You didn't consider fire spreading in the building, do you?
No, that's exactly one of, relates to your first question, you're absolutely right. That's why we assume different scenario. We have fire in terms of temperature conduction, right? That goes from the steel to the slab but we don't have the fire dynamics that takes into account the convection, how the wind is moving your fire within the building. No.
Okay. Thanks.
Yeah.
Thank you, Professor. My first question is with regard to the building level failure analysis. You, at the beginning, said that there's two major modes of failure, which is a column collapse due to buckling and then connections failing. You talked quite a bit about the column failing and proposed code revisions for addressing modulus and strength changes. What about connections? Have you guys had a chance to examine the code requirements for connections under failure conditions in fire?
Yeah, that's a good question. So that's a really nice question. For clarification, there was much more than two. You could end up with lots of possible failures. You could have, for example, local buckling. You could have local whip crippling, or you could have a bazillion things. But these are the two that we thought we need to look into. We looked at the columns only primarily, and we looked at the connection with the 3D finite element model. What we would like to do is ultimately have that performance-based design extended to an entire system level by developing models for the connections that can run very efficiently, as opposed to having a 3D finite element model that I showed. But we have not done that yet. It's functional funding. availabilities. Yeah.
Thank you. My second question is with regard to the community-based fire transmission. You said that there's the model is incredibly complex and it has lots of different parameters. So I'm assuming that's very time-intensive to input. Is it possible to generate an AI-based algorithm to analyze GIS information or meta information to perform community-based fire transmission?
Yeah, that's another great question. So setting up the model was difficult for us at the beginning, but now we've automated the process. So if we go to, for example, to something called OpenStreetMap. So we go to OpenStreetMap and automatically generate the entire community level parameters. Now, of course, you need more information on materials, right? If I will impose this radiation model, I need to have an understanding of what material is radiating on what material. And that information for residential wood buildings, it is available. For other buildings, that's not available. So the input parameters are very important. The model initially also required a lot more parameters for our radiation model that we developed, but we simplified that model further to exactly address your points. But again, and then we used neural networks to do an inverse calibration of the model to get all the parameters that we need to input to calibrate. Would this model work for another community with the exact numbers? Probably not. If it's a community that is built around the same time with the same material, the answer would most likely be yes, right? Another very important material, or shouldn't say material, but input is the vegetation, the type of vegetation, the probability of generating embers from these generated vegetation, and the volume. So we collaborated with a company that has done tremendous work on compiling all this data. It is very data extensive, yeah, fortunately.
With that, and thanks so much for the interest from the audience too. Great questions, but I'd like to very much thank our speaker,
Thank you
Professor
so much.
Mahmoud, for
Thank you.
coming today. So
thank you.
again,
Thank you so much. Thanks a lot.